Alright, so this is part 2 of the midterm review, and in this part we will go over graph theory. So the first one, you can see it has a graph of some states and ask you which of the following represent the state shown. Definitely this is going to be multiple choice on the test because as a computer test I just can't make you graph. So what you want to look for is the connections, and if you wanted you could kind of draw your own. Here's West Virginia, here's Virginia, here's North Carolina, here's Kentucky, and here's Tennessee. So using the same letters that were in the graph, and then also looking at kind of putting them in the same places that they have them. So West Virginia is touching Kentucky and Virginia. I can see that. Virginia is touching North Carolina, but it's also touching Kentucky. Kentucky is touching Tennessee. Tennessee is touching North Carolina. So that was just the easy glance. Now let's go back and check it. West Virginia definitely touching two places. I can see two connections. Kentucky, West Virginia, Virginia, and Tennessee, so it has three. That looks good. Tennessee is touching North Carolina, but I can also see Tennessee should be touching Virginia, so I need that side going through there. North Carolina is touching Virginia, Tennessee, and that is it. So I feel good about this. So now let's look at our choices, and I hope you can see it's pretty clear that A should be the answer. Alright, in number 23 it says use the graph to answer the question. So the first question says how many vertices are there? So vertices are the dots, so I have A, B, C, D, E, that's 5. And then how many edges? So I have 1, 2, 3, 4, 5, 6, 7. And I marked on it because that helps me like see like 1, 2, 3, 4, 5, 6, 7, so I didn't forget any of them, and I'm just going to erase the marks now because we don't really need them. Okay, so let's add my pen back. Alright, then it says for each of the vertices tell the degree. Alright, so in A I have 1, 2, 3. So how many edges does it touch? B touches 2. C touches 1, 2, 3. D touches 1, 2, 3, 4, and E touches 1, 2. So that's it on that one. Alright, and number 24 says how many degrees are in a graph with 13 edges? Well, you always have twice the degrees as you do the edges, so this is 26. And then it says how many edges are in a graph with 10 degrees, so that way I would divide by 2 and get 5. So there is this relationship. Twice the edges is the degrees, or the degrees divided by 2 tells me how many edges. Don't get those confused. I know they're close, but pay attention. Alright, 25 just says decide if it's connected or disconnected. 25 is connected. Everything I can get from one place to the other. But in the second part it's disconnected because it looks like I drew a triangle and then drew a line on top, and like I couldn't get from here to here no matter how hard I tried. This one's just going to go back and forth, and this one's just going to go round and round. In 26 it says determine if the sequence is a walk, a path, a circuit, none, and it can be more than one, so it says check that all that apply. And I'm just going to try using my highlighter going over it. Maybe that will help, and then I'll probably have to erase each one of them, but that's okay. So the first one says D to E. Whoops. It's not actually doing it. Well, I guess we're not going to use the highlighter because it doesn't want to. Let's see if I can write a different color. D to E, and then E to C, C to A to B, and then B to D. Alright, so that looks really good. That is definitely a circuit because it began and ended at the same place. Everything is a circuit is a path. Everything is a path is a walk. The next one said, and let's erase this other stuff so I can see better. So the second one says G to D to F to I. Well, immediately there's a problem. There's no way I can get from G here to D here. There's not a direct edge, and it would have to, so that's a none. Alright, the next one pretty long. It says A to B to G to I to F to D to B, and then through A again. Okay, This through A again is the whole issue with this one. That is not a circuit because I repeated an edge. So it's not a circuit, it's not a path, it's only a walk. A walk you're allowed to repeat. In a circuit and a path you cannot repeat. Again, let me get rid of all these markings I did. Alright, and then the last one says A to C. So here's A to C, to E, to F, to I. Alright, so definitely that one's a walk. They're all connected. It's a path because I didn't repeat. And that's it. It's not a circuit because I didn't go back to where I started. Well, let's go back to black for my marker. 27 says find any bridges, or say there's none. Alright, so definitely I have a bridge right here from A to E, because if I removed it, A would be isolated. Also, B to C is a bridge because it connects the two parts together. Sorry. Alright, so number 28, decide if each has an Euler path, Euler circuit, neither or both. So as I'm looking at these, I'm going to start counting. So this is a 1, this is 3, this is 2, this is 2. So I'm counting the degrees of all the vertices because that's really crucial deciding if it has an Euler path, Euler circuit, neither or both. It has to be all even to have an Euler circuit. So this first one doesn't have an Euler circuit. It can have 2 odd to be an Euler path, so this one has an Euler path. I don't have to find it, I just need to say that it has it. This one has 1, 2, 3. This has 1, 2, 3. This has 1, 2, 3. This has 1, 2, 3, and this one has 4. This has neither. Right? It had odds, which made it no Euler circuit. It has more than 2 odds, that means no Euler path. Alright, so this last one, which is kind of crazy looking, so here's a 2, 1, 2, 3, 4, here's 1, 2, 3, 4, here's 1, 2, 3, 4, here's 1, 2, 3, 4. Alright, all even says this has an Euler circuit, and it has an Euler path. All Euler circuits are Euler paths by definition, so this is really both. 29 says, use the following graph, find an Euler circuit that begins and ends with the vertex A. Alright, so the first one says there's no Euler circuits, but let's just count. This is 2, this is 4, this is 2, this is 2, this is 2. I know it has an Euler circuit. Let's get rid of that. So how about, can I go from A to B? So I'm looking at part B. A to B, to C to D, to B to E to A. That looks awesome. So let's just put a little check mark there. This one says A, B, C, D, B, A. I didn't use E, so that's not good. This one says A, B, C, D, E, no such thing, so B is the only one that looks good. I keep going through them just in case, like maybe, you know, you can mess yourself up and grab an answer too quick, so sometimes it's nice to go through everything. 30 says, use the following graph to answer the questions. So in 30 it says, find a Hamilton path from vertex C. So a path says I need to go through all the vertices. I do not need to return to the beginning one. I just need to go through everything. So here's what I see. Couldn't I just do this? So this is C, B, A, F, E, D. And when I look at it, that's the only thing I could do. You cannot go to A first because you left out B and you'd have to kind of, maybe you could. No, you'd mess yourself up. You really need to just do this one. This is the one. It's really like sitting in front of you, and that's the best thing to do. Again, I tend to write on this and then we need to erase it, so let's do that. And then let's look at the next one and let's pick a color. Maybe that will help. Alright, find an Euler path from vertex B. So here's B. This is where I want to start. Now notice that's 1, 2, 3, which is odd, and let's look at E is also odd. So I know if I'm starting at B, I'm going to end at E. That's what's going to happen. So when I look at B, I'm going to do this triangle first, just get out of the way. So I'm going to do B, C, A, B. So B, C, A, B. Or I could have gone B, A, C, B. That's okay. I'll write it down here, B, A, C, B. Could have done that too. And then after that, I got to get out of there, so I have to go to E in either case. Alright, then I have a choice. I could go up, F, A, D, E, F, A, D, E. So I went from here FADE, and I could say that here FADE. Or I could have reversed it. I could have gone DAFE. So look, there's this other choice. So from E, I could have gone DAFE. So I'm just showing you there are a bunch of different things that work here. Oops. I hope if I don't just write the same one again for you. That I could have had B, A, C, B, E, and then D, A, F, E. So you have some choices. I know that I've got the test written to, it'll work for you. I have a mixture of multiple choice and fill in, and if there's more than one answer, then I have more than one answer that's going to mark as correct, so don't worry about that. Alright, number 31. So this big old graph, it's a weighted graph. You can see that. And the first question just says, what's the weight of the edge BD? So here's B, here's D over here, and this big loop-de-loop on the outside, which is 105. That would be the weight. The second one says, what's the weight of AECA? So here is A. Let's locate E, and then C, and then A. So AECA, I can see I need to add 22 to 75 to 40. Let me grab my calculator, 22, 75, and 40, and it says 137. Alright, so let's get rid of those markings, because the next one I'm going to mark on it again. And the next one says, find the weight of the nearest neighbor circuit starting from A. So I'm starting at A, and I can see 85, 22, 40, or 10. I definitely want to pick 10. And now I'm at B, so I say, would I go 105, 15, or 18? So I say, well, let's go 15. Right on my 15. So I went from A to B to C. Now I'm at C. I have 40, 75, and 60, and I want to take the 60. Okay, so now that I'm here, I have choices of 34, 85, and 105. Now I need to always stay with the smallest one, but I also don't want to form a circuit until I've gone through everything. So when I'm looking, I go, what's the smallest? The smallest is 34, so let's go 34. And at this point, I've been to A, to B, to C, to D, to E. That's awesome. I just need to finish up. I go into A, which is 22. Okay, so I have 10, 15, 60, 34, 22, which says 141. Then in part D, again, let's erase. I don't like things to confuse you if I have too much going on. Part D says, tell me, using the cheapest link algorithm, what are the first two edges that we would select? So what we're looking for is what are the smallest two edges in the graph. So when I'm looking, definitely this 10 is really small. And then I also see 15 is really small. Now notice there's not a starting point given there. That's okay. So A to B, and then B to C. But I want to say them separately and say, okay, these are the smallest two edges. That would be my start. All right. And then in E, it says, what is the weight of the cheapest link circuit? So let's just go ahead and finish this one off is what it says. So I picked up the 10 and I picked up the 15. Now as you're looking, 18 is the next biggest, but I can't use it because B's already been used twice. So after that, I see 22. After that, I see 34. And then after that, I see 60. So in this particular case, I got the same thing, 10, 15, 60, 34, 22. So once again, I got 141. It doesn't have to be that way. It's just how it ended up this time. That you can see the 10, the 15. I got rid of the 18. I picked up the 22. 34 was next. If you tried to pick up 40, you can't because A has already been used twice. So 60 finished it up. Okay. And then, just to keep with the same thing, and let's erase everything I gave you so far, I said let's do the minimal spanning tree for this circuit. And again, I just want to know the weight of it. So remember with the tree, In this one, I have five vertices, so I'm going to need 4 edges. And I want to pick the smallest 4. So I'm going to pick 10. I'm going to pick 15. So right now it feels the same, except what will feel different is I can pick up 18 this time. So with trees, I can use a vertex more than twice, and I have. So now I have included the 18. I cannot use 22 because that would form a circuit, and that would be bad. So I go to the next one, which would be 34, and oh, look, I'm done. I have 1, 2, 3, 4 vertices. So this 10, 15, 18, and 34, there's my tree. So 10, 15, 18, and 34 gave me 77. So my minimal spanning tree would have a weight of 77. Alright, so this says how many edges enter a tree with 6 vertices. So that would be 6 minus 1 is 5. And then how many vertices are in a tree with 4 edges? That would be 4 plus 1 is 5. If you were to get confused or stuck on the test, why don't you just draw one? Right? If you get to this and it says how many edges in a tree with 6 vertices, I would draw 1, 2, 3, 4, 5, 6 vertices, and I would make a tree, and then I would count 1, 2, 3, 4, 5. Or if you had a tree with 4 edges, so maybe draw 4 edges, and then count 1, 2, 3, 4, 5. There's no reason to get yourself confused. You can always draw something if you need to. Alright, so this says decide if each one's a tree. So this one has a circuit, so this is a no. This one looks great, so this is a yes. Alright, this is a fill in the blank. A circuit that uses every edge of the graph exactly once is called a blank circuit. Well, every edge, that would be Euler. A circuit that uses every vertex, that would be Hamilton. Alright, this is a bit shorter because I did definitely double up, but that doesn't mean that graph theory is easier. I hope that you think it's easy though. So that's the end of our second part of the review.